Okay, so I'm going to take a look here at variance covariance. I'm going to estimate the variance covariance matrix for a portfolio stocks. I take this example from Simon Benninga's book, Financial Modeling, and it's on the 4th edition currently. So the thing I like about this particular example is the estimation of the variance covariance is important for a whole range of things, particularly for portfolio theory, and it's an important input into a variety of different other types of estimations that are done in finance. So the data that then we're given then, just to describe, we have annual data, and we're probably looking at the first trading day of each successive year here. So we have 11 observations. If we count here the number of observations that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's a 12 actual dates, which will give us 11 data points. And okay, if we were to look then at in terms of, again, this is not essential for strictly the variance covariance. This becomes more important for portfolio decisions, but we could say that we knew the number of stocks that there were, shares outstanding, number of stocks in millions, and then that would allow us to estimate, if you like, the market value. So if we just took the, in this cell here, again we're working in Google Sheets, we just took the value here of the stock price on the last trading day observable here in that column, the first column for General Electric, and multiplied by the 1056, which is probably 10.56 million stock, then we get a market valuation and we can pull it across. Okay, and again, if we want to then figure out what is as a percentage of the overall portfolio, if we were to weight each of these assets, General Electric, Microsoft, Johnson & Johnson, Kellogg's, I would imagine British Airways, perhaps IBM, BA, Boeing and IBM. So if you wanted to work out the weights then associated, we could take the market value. So we could take this value here, and then we could divide it by the sum of all the values in the row here. So if our portfolio was going to be made up entirely of these particular assets and we were weighting according to market capitalization. Okay, so if we double click here on this again and we put in dollar signs, right? The reason why we want to lock the cell reference here is because we want to just maintain let's try that again. And we put the dollar sign again around the G. Okay, and I'm doing it manually here. Okay, and then we pull across. Okay, and so what we basically have here is just the percentage. If we went by the market cap, then the percentage weight we might associate with each of the stocks, and IBM gets a slightly smaller weighting, and General Electric gets a slightly bigger. Now, General Electric is probably no longer a big a company as it used to be, especially compared to the early 2000s. Things have changed in General Electric, and of course Microsoft has been relatively robust and probably would still today have a fairly sizable market capitalization relative to the rest. So, and in any instance, we end up with these weightings based purely on market capitalization. That's not necessarily the best way to design a portfolio. But we're not specifically looking here at portfolio. We're actually trying to create a variance covariance matrix. And that normally entails taking the variance covariance of what? Well, it's really the return on the asset. Okay, so to get the return, now the return, note here this is 94, and if we come up above here, the starting would be 93. So basically the return has always lagged 1 year. So the return in 94 is what we observe in 94 divided by the previous year. And this is a log difference. Okay, and we can just very simply pull that across. And this gives us an annual return on each of the stocks, 1994 through to 2004. Okay, and figures here generally positive, but there was some negatives, right? There was some negatives, and the tech stocks, of course, were hit hard in after 2000. Okay, so then it's incumbent upon us then to estimate the average. So okay, we put in average, and we can use the same as before. We can take the average of these. Okay, and we get 2366, and we can go again and just pull across, and we get each of the averages. That's fine. And then what about the standard deviation? Well, that can be obtained. Standard deviation, open bracket, and then we just drag down, close the brackets, and we can drag across. So we get 3217. Okay, so these estimates are things we will look at as we proceed. And then to get the variance, well, we can just square. One way of getting the variance here is just to square the standard deviation. And a feature of the variance, when you have a percentage and you square it, tends to get smaller. Okay, so that's something that is worthwhile. Okay, let's just reframe that. So I'm expressing this in decimals, I'm expressing this in percentages. I suppose I could change it to, we could change it to percentage as well. Okay, 1035, 1657, and 3.6. Okay, so the variance looks smaller here than the standard deviation. That actually isn't too surprising. That's what we would expect once we're working with values less than 100%. Okay. So next thing then, in order to estimate the variance covariance, we have to estimate the excess returns. Okay, so to estimate the excess returns, we come here to B42 and we say equal to, and then we go back up, right? So we come back up here to our 56, the first return, and we subtract away the average return. Okay, and in that process, we will put in a dollar sign just in front of the 35. Now the effect of doing that is that when I drag across, then I've locked the cell reference, but we're able to update. So for instance, here we're subtracting negative, we have 1.5 negative, and we're subtracting away 2138, so we get that negative 22. Now we can pull that down and the columns are respected, but we're locking, so for instance here, if we come back here and come down for a moment and just observe what the estimation entails, we didn't alter this reference here. The 2366 is fine. We're still subtracting that away from the 1823. When we come out of that and come across here, same again, right? But when I go to the cell below, still the same average, but we've allowed the Microsoft year to update the following year. So that's why the single dollar sign here is beneficial. It partially locks the cell reference, not completely. Okay. So that gives us then, if you like, the excess returns, and then what remains to be done is to estimate the variance covariance matrix. Okay, so to estimate the variance covariance matrix, I actually want to multiply, right? We're going to do a matrix multiplication operation, and that's feasible we use the same commands, function names as in Excel. and we're going to multiply two matrices. In fact, we multiply the same matrix by itself, but in order to accomplish that, we have to transpose, first of all, transpose, P-O-S-E, this matrix here, and it's been multiplied onto itself. It's been multiplied and onto itself. So you only can multiply a matrix by itself if you transpose one of those matrices. And in order to take into account that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Because we have 11 observations here, we divide by 10, and that's equivalent to dividing by n minus 1. Okay, and we can return and we get a value, but obviously what we need is the full array. Okay, so we highlight everything again and we return. And we return by holding down on the keyboard Control-Shift-Enter, right? And we return. Okay, so I held down Control-Shift-Return, then I released, and then these figures became available. And what this represents here is the variance covariance matrix. Okay, the variance covariance matrix. Now, can we do a little test to ensure that the values we've obtained are consistent with at least do a kind of a check to verify that at least the variance diagonal is consistent with our previous variance estimate. Well, we had the variance here and here, so let's just check that this variance and this variance are consistent. This variance figure is consistent with this. The variance of Johnson and Johnson, Johnson and Johnson, Kellogg's, Boeing and Boeing, and IBM, those figures are consistent, right? So when we observe the variances, we can see in our variance covariance matrix on the diagonal we do indeed observe we have the correct values for the variance, because that's what we had estimated before. So those values are consistent. Okay, so we can, in a later video, I'm going to outline how we use this variance covariance matrix to estimate the variance and standard deviation of a portfolio, of the portfolio given.